All right, in our Sage interlude for section 1.4, we're going to just go over some basic modular arithmetic in Sage. So we know, for example, that in, say, Z mod 5, when you multiply 2 with 3, you get 6, and 6 is congruent to 1 mod 5. So we can actually do that in Sage. So we can ask it mod 2 times 3 and then 5. So in the first expression, we have the thing we're trying to compute, the the conjugacy class in Z mod 5 for, and then we have to tell it the modulus. So we have to tell it we're actually looking in Z mod 5. If we evaluate this, we should get 6 mod 5, which is 1. And in fact, we do. And actually, what this is telling us is that 2 is the multiplicative inverse of 3 mod 5, and similarly, 3 is the multiplicative inverse of 2 mod 5. Because when we multiply them together, we get 1. Now, let's look in mod 6. Now, 2 times 3 is 6, and 6 and 0 are the same mod 6. So we should get 0 when we compute that. And we do. Great. So here is the expression you want to reduce. And in this part, this is the modulus. So that's how this mod parenthesis operation works. There's actually another way of going about this, which uses the fact that the modulus is really just a remainder. To find the equivalence class between 0 and n minus 1, you just look at the remainder mod n. And so, for example, we could look at the remainder of 6 mod 5. So 6% 5 says, give me the remainder when I divide 6 by 5. And you get 1. If we do 7, we should get 2. If we do 8, we should get 3. If we do 9, we should get 4. And when we do 10, we should go back to 0. And we do. So this percent symbol is carrying out what we were doing with this mod function. Now, you can also do inverse mod whatever. So let's try 2 and 5 here. So again, the second argument is the modulus. And this is saying, give me the multiplicative inverse of 2 mod 5. What we should get out of this is 3, because we know that 2 times 3 is 6, and 6 is 1 mod 5, and we do. Similarly, if I put a 3 here, it should give us a 2, because 3 is 1 over 2, so 1 over 3 should be 2. And in fact, it is. 4 is its own inverse. 4 times 4 is 16. 16 mod 5 is 1, so it should give us 4. And same with 1. And I actually don't know what kind of error it's going to throw or what it's going to tell us with 0. Oh, here we go. We have a 0 division error. Okay. So that makes sense. Now, I also don't know what's going to happen if we do 2 mod 6. It's not 2 doesn't have a multiplicative inverse mod 6 because 2 is what we'll call in class a 0 divisor. So it's impossible to undo to multiply by 2 by something and get 1 mod 6. And let's see what the message that Sage gives us is. So what do we have? Another 0 division error. Does not exist. Okay, great. Now, if we instead did 5, this should be okay. 5 times 5 is 25. 25 mod 6 is 1. It's just the divisors of 6 are going to be the problem. Or anything that has any common prime factor with 6 is going to be a problem. So we can also do inverse mod if we like. So just to be clear, we've talked about 3 things. We've talked about the mod function to do modular arithmetic. We've talked about how it's kind of the same as the percent function. In fact, you can do stuff like 2 plus 6 times 5 plus 3 mod, I don't know, 21 if you like. It doesn't matter. This will give you the same effect as the mod function. And there's also the inverse mod function, which will compute multiplicative inverses when they exist and will error out when they don't exist.